Inverse functions, section 11.6. Recall a function sends one value in the domain to one and only one value in the range. A function sends, again, only one value in the domain to one and only one value in the range. A one-to-one function is a function that has every element in the range corresponding to at most one element in the domain. At most one element in the domain. What does that mean? Well, in other words, for each f of x or output, there is only one input x that will yield our f of x. That essentially means for each output f of x, there is only a unique x. There's only one. There's only one x that will give me this f of x. Remember, f of x is equivalent to the output y. So if you look at a set of ordered points, there is only one x that when you plug it into the function f of x, you're going to get a y. There's only one x that would give us that y. To understand the concept of functions a little bit better, let's determine whether the function represented by the set of ordered pairs is a one-to-one function. I would like to draw some pictures to demonstrate if this is a one-to-one function or not. Negative 7 gets sent to a negative 5. Negative 5 gets sent to a negative 2. Negative 2 gets sent to a 4. 3 gets sent to 3. And 6 gets sent to a negative 7. Notice that for every single one of these outputs, there's only one number that would give us a negative 5 for the output. There's only one number that would give us a negative 2, and that's negative 5. Only negative 2 will give us a 4, 3 gets a 3, and negative 7. There's only one number that would yield negative 7. So this is in fact a one-to-one function. This is similar to the vending machine analogy. This is an example where each person bought a unique item at the vending machine, so this is a one-to-one function. Let's look at example 2. We have the ordered pairs, negative 4, negative 9. That means negative 4 gets mapped to negative 9. Negative 2 gets sent to a negative 7. A 1 gets sent to a negative 6. So we're doing okay so far, but a 2 also goes to a negative 7. A 6 gets mapped to a negative 11. So this is a function. This is definitely a function. What is the definition of a function? For each input, there is only one output. Well, each one of these has one output. Negative 4 gets sent to negative 9. Negative 2 gets sent to negative 7. That's just one output. 1 gets sent to negative 6. That's okay. And 2 gets sent to one output, negative 7. So it qualifies as a function. But a one-to-one function is special. A one-to-one function is more special because for each of these outputs, you can only have one unique input that will work. But we have a problem. If you look at negative 7, you have two different inputs that still gives us the same output. So this is not a one-to-one function. In example 3, 0 gets sent to 1, 1 gets sent to 3, 2 gets sent to 9, 3 gets sent to 27, and finally 4 gets mapped to 81. Each of these outputs has only one input that corresponds to it. So this is definitely a one-to-one function. Now we can actually use a test to determine if a function is one-to-one. That's called the horizontal line test. If a horizontal line can intersect that graph at more than one point, if it intersects a graph at more than one point, the function is not one-to-one. So if you can draw a horizontal line that intersects twice or more, it disqualifies it as a function. Let's look at this example. Just one. We only need one line, and I'll pick a random one, this one. You can see that it intersects twice, so this is not one-to-one. This is not a one-to-one function because I can draw a horizontal line that intersects more than once. This is not one-to-one. If I look at part A, is the following functions one-to-one or not? I can draw again a line that intersects twice, so it disqualifies it as a one-to-one function. So we'll write it's not a one-to-one function. In part B, if you draw a horizontal line, it doesn't matter how many you draw, you'll never find one. You'll never find one that intersects more than once, so this qualifies as a one-to-one function. Now, why do we care if a function is one-to-one or not? Well, if a function is one-to-one, that means an inverse function will exist. A one-to-one function implies that an inverse function exists. So if you have a function that is one-to-one, we know there's going to exist an inverse function. Inverse functions undoes what a function does. For example, if you have a function that takes an a to a b, the inverse will go backwards. It would take a b back to an a. That's the operation of the inverse function. For example, let's consider the point 3, 7. The 3 gets sent to a 7. But what would the inverse of f of x do? It will send the 7 back to a 3. So here's a picture of what's happening. The original function f of x would give us a 7. So that's saying f of 3 would give us 7. But the inverse of f of x, the inverse of f of x, which we will denote with this -1 here, the inverse of f of x would send that 7 back to a 3. And so this is our notation. It looks like an exponent, but it's not. This means the inverse. So this is the inverse of f of x. So the inverse of 7 will give us a 3. So let's consider what the inverse would do to these points. The inverse would take a 7 and send it back to a 5. It would take a 3, which is the output, and send it back to an 8. It takes a 2 and send it back to a 9. So again, it's doing the opposite. It's taking the output and giving us the input. So we'll take the 12 and send that back to a 10. This is the inverse of our ordered pair. We have a property of inverse functions. Two one-to-one functions, f of x and g of x, are inverse functions if f of g of x is equal to x and g of f of x is equal to x. So both of these cases must be true for these two functions to be inverses of each other. So let's determine whether the two functions are inverse functions. We'll start by finding f of g of x. That means I'm going to take the f function and substitute the entire g into it. This is the function g. We're going to take that whole thing. We're going to plug it back into this x. That gives me 5 times. We're going to do a substitution with x plus 2 over 5. And then we'll simplify. The 5's reduce. And so we have x plus 2 minus 2. This cancels out. And we do get an x. That's great. We have the first condition met. Now we have to do the opposite. G of f of x. So this means the entire function g is going to eat the function f. So f is going inside g this time. That means this whole thing gets plugged into the x of the other function. That means we have 5x minus 2 plus the 2 is divided by 5. This is the substitution that we did. Sometimes it's necessary to put parentheses, but in this case there's nothing multiplied to it, so we can remove the parentheses. And if you remove the parentheses, you can see that the 2 and the negative 2 does cancel out, leaving us with 5x divided by 5. And that simplifies. That simplifies to just x. So both of the conditions are met. That means they are inverse functions. One function does the opposite of the other function. Let's look at example 6, and we will again try to show f of g of x is equal to x. That means f of g of x tells me I have to substitute that g into the function of f. So g is going to go inside f. That is 4x plus 7 minus 7 divided by 4. Again, I don't really need parentheses because there's no multiplication done to the 4x plus 7. You'll see that the 7 and the negative 7 cancels out, and you are left with 4x divided by 4, which simplifies to x. So the first condition's met, but we still have to check g of f of x. This means g is going to eat the f function. And so the whole thing, x minus 7, gets plugged into the x this time. So we have 4 times the quantity, x minus 7, divided by 4. In this case, I do need the parentheses. We're multiplying with a 4. And then we'll add the 7. The 4 and the 4 does divide out. You get x minus 7 plus 7. And so again, we have this is equal to x. So these are inverse functions. These two are inverse functions. Example 8, we'll try this again. We'll see if these are inverse functions of each other. We'll look for f of g of x, which means the entire function g gets plugged into here. That's 1/3 times 3x minus 12 plus 4. But that means I have to distribute that 1/3. 1/3 times 3x, that's x. 1/3 times negative 12, that's negative 4. So this does reduce to give us x. Let's check the other side. G of f of x. This means the g function is going to take in the f of x function. So this time we're going to take 1/3 x plus 4. I'm going to substitute it into the x for the g of x function. This gives me 3 times 1/3 x plus 4 minus 12. I can distribute the 3. And so 3 times 1/3 x is x. 3 times 4, that's 12. 12 minus 12 gives us just x. That means these two are again inverse functions of one another. So they're both inverse functions of each other. Example 9. To check if these two are inverse functions, you have to compose them again. F of g of x means the g is going inside the function f. This is 6 times 1 over 6x plus 3 plus 18. I have to distribute that 6 now. 6 times 1 over 6x, that will reduce to x. 6 times 3, that's 18. And we have a plus 18. So this simplifies to x plus 36. But we were supposed to get f of g of x is equal to x. And that would imply that it could be a one-to-one function. But we didn't get that. We did not get this case. This is not what we have. So this doesn't work. What does that mean? Do we have to check the other side, g of f of x, to make sure that's x? Do we have to check that? No, we're done. If one side fails, this fails, it's not equal to x, it doesn't matter what the other side is. These two are not inverse functions. They're not inverse functions. So if one side failed, it doesn't matter what the other side is. These are not inverse functions. How do we determine the inverse of a function if we're just given one function? This is the process. To find the inverse of f of x, determine whether the function f of x is one-to-one. Again, you can only find an inverse if the function is one-to-one. And you can check that by using the horizontal line test to determine if this function is one-to-one or not. If it is not one-to-one, then it does not have an inverse function. We start by replacing f of x with y. And then in step 3, we interchange the x and y, which means we're going to swap them. We interchange these two variables because we know that the input f of x must be the output of the inverse. And the output of f of x must be the input of the inverse. Solve the resulting equation for the y. This allows us to express the inverse function as a function of x. And then finally, at the end, don't forget you have to replace the y with the symbol for the inverse function. So let's try some examples so we can get a better grasp of this section. To find the inverse function for f of x, you have to determine if this thing is one-to-one. We are going to assume that these functions are all one-to-one, and we are going to look for the inverse. To find the inverse, we start by replacing this f of x. I'm going to replace it with the letter y. That's the second step. We already have the assumption that it's one-to-one. The second step is to replace f of x with y. And then the third step is to swap the x's and y's. So what we did first is we replaced f of x with y. And now you're going to swap them. You're going to replace the x with y and the y with x's. This is going to give me an x equals 1/2 y plus 10. Why do we switch the variables? Well, we're going to do the opposite, which is the inverse. The inverse does the opposites, and so that's why we are swapping the variables. Now let's solve for y. And to do that, I will subtract 10 to both sides. Let's subtract 10 to both sides. And so that gives us x minus 10 is equal to 1/2 y. We can now multiply both sides by 2 to get rid of any fractions. And that means I need to distribute this too. So that's 2x minus 20 is equal to, well, the 2 and the 2 here reduces to just give us a y. And the final step of this is to replace the y gets replaced with f inverse of x. So the final step is to replace the y with f inverse of x. So my final answer is f inverse of x is equal to 2x minus 20. That's my inverse function. Example 11. Again, we're going to assume this is 1 to 1. So the next step after that is to replace f of x with y. And this becomes y equals 4x plus 7. After you do that, you're going to swap the letters. Just switch them around. Y is replaced with x, and x is replaced with y. After you do that, you're going to have to solve for y. Let's subtract that 7 to both sides. X minus 7 is equal to 4y. And now I got to solve for y, so that means I need to divide both sides by 4. And y simplifies to x minus 7 over 4. But we're not done yet. We got to replace the y with the inverse symbol for the inverse function. And so my final answer is f inverse of x is equal to x minus 7 over 4. This is the inverse function. Let's try something more challenging now. Example 12. Let's start by assuming this thing is 1 to 1. And we can check that by using a graphing tool to graph this function and making sure it passes the horizontal line test. So let's have the assumption it is 1 to 1. And we'll start by replacing f of x with the letter y. So y equals 8 divided by x plus 1. Now we can swap the letters. X and y are swapped. X is equal now to 8 divided by y plus 1. I have to solve for y, so we'll multiply both sides by y plus 1, and that's going to essentially get rid of this denominator for us. This reduces. And so we have y plus 1 times x is equal to 8. But that means I could distribute that x. And so we have xy plus x is equal to 8. Let's start subtracting x to both sides to isolate that y. Xy is equal to 8 minus x. And now y is almost by itself. What do we got to do next? Let's divide both sides by x. And now we get y equals 8 minus x over x. But we're not done yet. You still have to replace that y with f inverse of x. So the inverse function is now equal to 8 minus x divided by x. This is my inverse function. Let's look at another example of finding the inverse function. Again, we'll assume this function is 1 to 1, and that means we'll start by replacing f of x with y. This becomes y equals 3 plus 5x over x. And now the next step is to swap the letters. Let's switch them around. X is now equal to 3 plus, well, there's two x's, so we need to replace both of them with the letter y. I want to get rid of fractions. Let's multiply both sides by y. We'll multiply both sides by y to get rid of this fraction, and it does reduce, which means it simplifies to xy equals 3 plus 5y. Now the goal is to solve for y. We have to solve for y, so let's at least get it to the same side. Let's subtract 5y to both sides, and this cancels out. Our equation becomes xy minus 5y is equal to 3. Now this is the part where we have to solve for y, but there's two y's that show up. How do we get them to be 1y? Well, the best way to do this is to factor. We can factor the y's out to the front. Let's use factoring. Y goes to the front, and that leaves us with an x and a negative 5. So this is x minus 5 on the inside equal to 3. If we're not sure this is correct, you can distribute that y and you'll get the previous line. And it works. So this is a correct factorization of the previous line. What do we do next? We have to get that y by itself, so I need to get rid of this x minus 5. Let's divide both sides by x minus 5 to isolate the y. And this simplifies x minus 5 divide out. So we have y equals 3 divided by x minus 5. And of course the last step is to replace that y with the inverse symbol. And then we're done. So this is the inverse function now. F inverse of x is 3 divided by x minus 5. In example 14, this is going to be challenging, but it's still the same process. We're going to replace f of x with y, and so this becomes y equals 7x plus 6 divided by 5x minus 3. The next step is to swap the letters. Let's just switch them around. And just like in the previous example, we're going to replace all of these x's with the letter y, and all of the y's with the letter x. And we're going to have to solve for y now. To do that, we'll get rid of this fraction, multiply the top right here by 5y minus 3 on the right. And on the left, we do the same thing. We multiply 5y minus 3 on the left. And that is going to reduce the right side so we don't have any more fractions. So that simplifies to 5y minus 3 times an x equals 7y plus 6. We'll have to distribute the x now throughout here. And that gives us 5xy minus 3x is equal to 7y plus 6. Just like in the previous example, we want the x on one side of the equation. So we want the y on one side of the equation. That means we need to add and subtract some terms. I'm going to subtract 7y to both sides first. And that's going to cancel this out. But I want to get the x's on the other side, so let's add 3x to both sides as well. And that cancels out that 3x and the negative 3x. This simplifies to 5xy minus 7y. It's all on one side now. Equals, and on the right you just have 6 plus 3x, or I could write 3x plus 6. Just like in the previous question, we're going to factor this y out. Let's take out the y, leaving me with 5x minus 7 equals 3x plus 6. Now we can divide both sides by 5x minus 7. And we get y is equal to 3x plus 6 over 5x minus 7. We're not done yet. You always have to replace that y with the inverse. So we have the inverse function is 3x plus 6 divided by 5x minus 7. In the next exercise, let's find the inverse function for f of x equals the square root of x plus 4 minus 2. And we also want to state the domain of the inverse function. The first step is, again, we want to replace that f of x with the letter y. So we'll do that now. This is y equals the square root of x plus 4 minus 2. And then you're going to have to swap the letters. We'll replace this y with an x and this x with a y. Then we can add 2 to both sides. We'll add that 2 to both sides. This cancels out. So my equation becomes x plus 2 is equal to the square root of y plus 4. Remember how to get rid of the square root? You have to square both sides of the equation. We have to square both sides of the equation. And this gives me an x plus 2 squared equals the right side, which just cancels out the square root, or y plus 4. Now we could FOIL the x plus 2 squared out if we wanted to, and you definitely could. But I'm going to leave it alone. We still have to solve for y, so let's subtract 4 to both sides. And this gives me y equals x plus 2 squared minus 4. And now you can see why I didn't FOIL out x plus 2 squared, because it's in that nice vertex form that we like. We can tell where the vertex of this parabola is. This is our final answer. F inverse of x is equal to x plus 2 squared minus 4. So this is it. This is our solution, the inverse function. I want to see what the difference between the function and the inverse function is. So I want to graph them on the same graph. So let's look at this function. We have the square root of x plus 4 minus 2. Recall h comma k is going to give us the location of the endpoint, and that's a negative 4 and a negative 2. We'll go to negative 4 comma negative 2. And if you don't remember this, please review graphing square root functions. And we'll look at the parent graph for the square root function. We picked points 0, 0, 1, 1, and 4. The square root of 4 was 2. So if you remember the parent graph, we go to the right 1, up 1, to the right 4, up 2. And so this is the original graph. This is the square root function. It looks like a sideways parabola. But what does the inverse function do? Well, in order to find the inverse and graph it on here, what's really nice is I can look at the points. This is the point negative 4 comma negative 2. This is the point negative 3 comma negative 1. And the last one's the point 0 comma 0. The inverse, recall, is going to swap this. So the inverse is going to take a negative 2 and send it back to a negative 4. A negative 1 and send it back to a negative 3. 0 goes back to 0. So let's graph the inverse on the same plane. And so we'll start by 0, 0, so that overlaps. We have a negative 1, a negative 3. And we have a negative 2 comma negative 4. So it looks like the same graph, but it's reflected. It is reflected. It is reflected about this line, y equals x. So the function is the blue, and in red we have the inverse. The inverse is reflected about this line, y equals x, and that's always the case for inverse functions. Now let's look at the domain for the original function. The domain for the original function, the blue function, goes to the left negative 4 and to the right forever. The range for the original function goes down to negative 2 and up forever. But what about the inverse? What about the inverse of f of x? The inverse would have a domain, if you look, from negative 2, it goes to the negative 2 to the left, and it goes to the right forever. It goes down to negative 4 for the range, and up forever. So what's the difference between the domain of the function and the domain of the inverse? They're swapped. They're switched. And why are they switched? Well, we replace the x with the y and the y with the x. So it makes sense. So the domain of the original function is our range, and the range of the original function is our new domain for the inverse. Find the inverse of the function from its graph. To do this, I'll look at nice points on the graph. This is a nice point. This is 0, 6. And this is also a nice point. Let's call this one 4, 0. We could try to find another one. This looks like 2, 3 to me. What does the inverse do? The inverse swaps them. 6 goes to 0, 3 goes to 2, and a 0 goes to 4. So I could just graph the points, and we know it's going to form a straight line, so I only needed to pick 2 points, but we just picked more just in case. And so we do have a nice straight line, and this is our inverse function. And if you were to plot these two graphs on the same graph, you'll see it is reflected. It should be reflected about the line y equals x. This is a square root function. And to find the inverse, we start by looking at this point. This is the point -6, -3. This looks like the point -5, -2. And the last one here looks like a good point. This is the point -2, -1. But what is our inverse function going to look like? Well, it's going to send -3 back to -6. It's going to send a -5, or it's going to send a -2 back to -5. And finally, it's going to take a -1 back to a -2. So let's graph our inverse function. We'll start with -3, -6, -2, -5, and -1, -2. So we have a square root function, but it's kind of turned around, and this is our inverse function. If you want to find the domain of the inverse function, we can look at the graph. It goes to the left all the way to -3 and to the right forever. The range, well, it goes down to -6 and it goes up forever. This is our range. For our last example, we'll again find these nice points that we are given. This is the point 2, 0, 3, 1, 5, 2, and the last one is 9, 3. What would our inverse do to these points? It's going to swap them. 0 gets sent to a 2, 1 gets sent to a 3, 2 gets sent to a 5, and the last one, we're going to have a 3 gets sent to a 9. So we can plot these points now and finish this problem up. 0, 2, 1, 3, 2, 5, and 3, 9. And it should look like a nice smooth curve. We'll try our best to connect all of the points. And there is our graph.